Hello everybody and welcome to Notes 7.2. Today we're going to be talking about the properties of exponential functions. So let's go ahead and get started. So like always, we always have a parent function. So for the exponential functions, we have y equals b. b represents your base to the x power. Your base will change. So this is the first function that we've really looked at where the parent function is going to be different for each graph because the bases will change. Your base could be 2, your base could be a half, your base could be 5 halves, whatever the case is, b is going to change. So we don't have that like standard parent function that we've had in the past where the graph is the same for every single parent function. So this is the first time our parent functions are going to change, and this is the first time that I actually like using t-charts for these types of graphs. So the next thing we have is with a stretch. So remember, a stretch is going to happen when we have a being multiplied to the front, and a needs to be greater than 0. So the absolute value of a is greater than 1. Okay, so we would have a shrink if a is in between 0 and 1. Again, we talk about the absolute value because if there is a negative, that is a reflection. So for a reflection across x, we have y equals a b to the x, and now your a is going to be less than 0. Or in other words, it's going to be a negative number. And then we have our translations that we've been practicing all year. So our translations are y equals b. Inside the function is now in the exponent. So we're going to have x minus h and then plus k. And then all of our transformations combined, we're going to have that y equals a times b to the x minus h power plus k. And that's going to give us all of our transformations. The next thing we're going to talk about is a natural base. So we have this natural base. We'll go ahead and highlight this. This is something new that you guys haven't seen. So when we have a natural base, that's a base of e. So the natural base exponential function is y equals e to the x power. E is the same idea as pi. So we have this irrational number that goes on forever and ever and ever and ever, like pi, but e is approximately, see here. Oh, let's actually move that. Let's write it down here. So E is approximately 2.71828 ... goes on forever and ever and ever and ever. E is irrational. Okay, E came about when we talk about compounded interest. That's where E came about, and that's what we use it for. So the next thing we're going to talk about is continuously compounded interest. Let me just, there we go. So continuously compounded interest, so it's constantly compounding its interest. That is we're gonna use PERT, and I call it PERT. So it goes A, which is the value in your account, equals P. P is your principal. E is that natural base, raised to the RT. So I call it PERT. R stands for rate, T stands for time. So we have your total amount is equal to your principal times E. So E is that 2.7 raised to the rate times time. And then we have this half-life formula also. So we're going to have half-life is your final amount, so A to the F, that's your final amount, is equal to your original amount, so A0 or AO, our original amount, times 1/2, that's why it's called the half-life, to the T divided by K, and K is your, whatever the half-life is. It'll tell you what the half-life is. So these are going to be the formulas that we're using for today's lesson. So let's move on to example 1. And in today's lesson, we are going to be using a calculator. I'm going to be using an app on my iPad. If you guys actually have the TI-84 calculators, have that out and ready as well. So we're going to go ahead and compare the graph of y equals -1/2 times 2 to the x power to the parent graph y equals 2 to the x. So we're going to go ahead starting by graphing our parent function. This is the one time that t-charts are actually really useful, and we're actually going to want to use those t-charts just because my base keeps changing, so it's going to be useful. So we're just going to start plugging in for that parent function. So we're going to get 2 to the -2 power. I'm just going to do like a little thing. 2 to the -2. Remember, whenever you have a negative exponent, to make it positive, it moves it to the denominator. So we're going to really have 1 over 2 squared, which is going to give me 1/4. So this would be 1/4. Okay, to the -1, that means we're going to move it down to the denominator. So now we're going to have 1 over 2 to the first power, which is 1/2. To the 0, anything to the 0 power is 1. And then we're going to have it to the first power. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. So this is going to be my parent function. All right. Let's go ahead and graph those. I will graph it in purple. So we're just going to plot those points. So at -2, I'm at 1/4, and then 1/2, and then at 1, I'll zoom in for you guys. And then we're at 2, 4, and 8. Okay, so I'm going to connect this with a dotted line, and it is approaching 0. I make that dotted because that's not my final graph. That is just my parent graph. All right, so now let's talk about the transformed one. So this is my transformed one. Let's talk about all of these transformations. So a negative out front is a reflect across x. Okay, the 1/2 is going to be a vertical shrink, because it's in between 0 and 1, by 1/2. And that's the only thing that's happening here. There's no right lefts, there's no up downs. Okay, so since there's no right lefts, there's no ups downs, our asymptote's going to stay the same. So remember, on these graphs, we have a horizontal asymptote. It's what it approaches. So on any of the parent functions, it always approaches 0. So as you guys can see here on this graph, it's getting really close to 0, but it will never be 0, or it will never cross 0. It'll just get continuously getting closer and closer and closer. But again, it will never, ever be 0. Okay, so on the parent function, our asymptote's always at y equals 0 right here. Since this one did not move up or down, so the only thing that's going to change it is if it shifts up or shifts down. The whole graph will push up or push down. That's when our horizontal asymptote will change. So since this has no up or down movement, my asymptote is still at y equals 0. In my class, for me, I like the asymptotes to be highlighted. So you guys are going to go ahead and highlight your asymptote. On Alex, you guys will have the option to put in an asymptote, so you guys will need to make sure you put in those asymptotes. And this is going to stay the same, so it's still going to reflect it. Or it's still going to approach it, not reflect it. I'm thinking ahead of myself here. All right, so with this graph, we can continue to use the t-chart method, totally fine. Or since we already have our parent function, we can actually graph it just using our transformations. I'm going to do that, and then we'll go back and fill out that t-chart. So for this guy, the first thing is it's going to reflect. So it's now going to go this way. It reflects across x. So all of these points are going to reflect across the x-axis. The other thing that's happening is my vertical distances are being cut in half. So we're going to go ahead and plot these. So the first one, we'll go here. This first guy is going to reflect, and then that distance is going to be cut in half. So our point would become right here. My next point, okay, it's going to reflect, and then that distance is going to be cut in half. So then I have a point here. Same thing, following this pattern. So this guy is going to reflect, and then the distance is going to be cut, reflect right here, and then the distance is going to be cut in half. So now it's going to be here. So we're 4, so it's going to be down to 2, like so. Next one is going to reflect and then be cut in half, so then it's going to be at 4. And then these ones are just, again, approaching, getting really, really close. So let's go ahead, connect it. Again, do not cross, don't ever cross your asymptote. You're going to approach it, it's going to get really close. And then let's go ahead and have those arrows on both sides of our graph. You know what? Let's actually put one more point. Okay, let's add one more point to this one. We can go ahead and do 4, so, and then cut it in half. So when we do 2 to the 4th power, so that's 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and then we're going to cut that in half. Half of 16 is 8. So we're going to get 4, negative 8 for our next one. All right, now let's connect it. I'm using a solid line to show that this is my final graph. And that's what it's going to look like. All right, let's go ahead and show that we could have used a T-chart for this whole thing. So again, we're just going to plug in and then multiply it by -1/2. So we already know right here, 2 to the -2 is 1/4, and then we need to multiply 1/4 by -1/2, which is going to give me -1/8. So you're pretty much just taking all of these numbers right here, and we're going to multiply by -1/2. So my next one, positive 1/2 times -1/2 is -1/4. 1 times -1/2 is -1/2. 2 times -1/2 would give me a -1. 4 times -1/2 would give me -2, and 8 times -1/2 is going to give me -4. So the T-chart will also work. We have these exact same points here. All right, let's go ahead and try our next one. So this one is going to give us that shift right and left. It's inside the function, so we're going right and left, opposite of what you think. So this is going to go left, left 2. Again, I have no ups, downs, so that means my asymptote is still at y equals 0. So we will go ahead and start again with our parent function. Again, your parent function is changing based off of your base. So we have y equals 3 to the x power. Remember, so when I have 3 to the -2 power, then we move it across the fraction line, so it's going to go to the denominator. So I really have 1 over 3 squared, and 1 over 3 squared is going to give me 1/9. And then we would have 1/3. 3, or anything to the 0 power is 1, 3 to the 1st power is 3, 3 squared is 9, and 3 cubed is 27. Okay, so again, with this graph here, we're going to go left 2. We did not go up or down, so asymptote is still at y equals 0. All right, I guess we can do that. We'll go ahead and do the T-chart method first this time. So this is inside. So ultimately what's happening is it's going to change our x value. So when we plug in, for instance, -2, we're going to get -2 plus 2, which is 0. And so 3 to the 0 power is now going to give me 1. And then we're going to have -1 plus 2 is 1. 3 to the 1st power is 3. And then we're going to have 0 plus 2 is 2. 3 squared is 9. Notice what is happening here. All of these are moving 2. Okay, so the next one would be 27. The next one would be 81. And the last one would be 243. Okay, when I graph this, I'm just going to go ahead and graph the parent and then shift it all over or all left 2. So take a highlighter or highlight your asymptote. Okay, and then I'll zoom in here. So for our parent function, we had -2 1/9, so just really close to 0. And then we had -1 1/3, so right about there. And then we have 0 1, and then we have 1 3, and then we had 2 9, and 327 doesn't fit. Okay, so this right here is my parent function. Again, it's dotted because it's not my final graph. So now all we have to do is take all of these points and move them left 2. So we'll just take them, shift them all left 2. So now we have a point here, point here, here, here about, and again, it's just going to approach that horizontal asymptote of 0. So connect it. Approach, don't ever touch or cross that asymptote. So it's just going to go and it's going to get closer and closer and closer to 0, but it will never cross it or touch it. All right, let's go ahead and move to the next page. So, using a graphing calculator. We don't need a graphing calculator for this. We're going to do this by hand. We definitely don't need a graphing calculator. So, we're going to go ahead and graph y equals 3 times 1/2 to the x power plus 2. Describe how this graph compares to the parent function. This is actually all the things I want to answer on this one. So, just copy this down for right now. So, I want to know, what is the parent? Is it a growth or a decay? Is there a stretch or a shrink? What is our horizontal asymptote? What is our domain? What is our range? What is my HK value? And what's my y-intercept? So we are able to answer all of these things without a graphing calculator. Definitely don't need that. All right, so let's go ahead and start answering these questions. So parent function, that's your base to the x power. So the parent function is going to be y equals 1/2, that's your base, to the x power. Put it in parentheses so that x is being applied to the 1 and to the denominator of 2. No parentheses, you're just implying that the 1 is to the power. Okay, is this a growth or a decay? So you check your growth or decay based off of your base. So if your base is a number greater than 1, then it's a growth. So if you had 2, 3, 4, 5, 6. It's a decay if it's between 0 and 1. So if you have a half, a third, 2/5, it's all less than 1, then that is going to be the decay. So since this is 1/2, this is a decay. Okay, now I want to know, does it stretch or does it shrink? So this guy stretches. And what does it stretch by? It stretches by 3. This right here is my stretch. All right, where is my horizontal asymptote? So again, our horizontal asymptote on the parent is always at y equals 0. The only thing that is going to affect that is a shift up or down, because you're going to push the whole graph up or the whole graph down. So that affects that range and it affects that horizontal asymptote. So if you look at this problem, this is going up 2. It's on the outside of the function. So that means it's a vertical and it's the same as what you think. So it's a vertical shift up 2. So our horizontal asymptote is also going to take the same thing and it's going to shift up 2. So this is also going to move up 2. So now we're at y equals 2 for my horizontal asymptote. Domain and range, I guess we can answer that after we actually graph it. You should be able to answer it without graphing it. And then h, so h is always going to be found up in your function. There's no value being added or subtracted up here, so the h value is 0. K is always your ups, downs, so it's going to be positive 2. So our hk is going to be 0, so h is 0, k is 2. And then our y-intercept. So remember, you can always find a y-intercept by plugging in 0 for x. So if I plug in 0 for x, anything to the 0 power is 1. So this is 3 times 1. 3 times 1 is 1. Or 3 times 1 is 3, plus 2 is 5. So our y-intercept is at 0, 5. All right, let's go ahead, graph it, and then we'll answer our domain and range so we can visually look at it as well. So I'm going to go ahead and start by graphing my parent, and then I'm going to use my transformations. So for the parent, we're going to need t-charts because our parent is changing every single time because the base changes. So our parent function is y equals 1/2 to the x. So we're going to pick values of x. So you want to pick things that you can easily do. Since this guy is a decay, that means this side over here is high and then it goes low. So when you have numbers over here, you're going to actually be able to multiply them and get bigger numbers rather than having all these fractions over on this side. So we actually like the negative numbers on this one. So let's start with -3. So remember, whenever you have something to the negative, and let's take my own advice and put parentheses on that. That's ugly. I gotta fix it. Here we are. So our parent is going to be y equals 1/2 to the x power. Okay, so since this is to the -3 power, what's going to happen is that fraction's going to flip to make the exponent positive. So really, this is just 2 cubed. And 2 cubed is 8. Okay, then I'm going to pick -2. Again, the negative is going to flip the fraction, so now this is really just 2 squared. 2 squared is 4. -1, flip the fraction, this is 2 to the first power, which is 2. 0, anything to the 0 power is 1. And now when we pick 1, so 1/2 to the first power is 1/2, and if we squared it, I would get 1/4. All right, this is my parent. Let's go ahead and plot these points. So we're at -3, 8, -2, 4, -1, 2, 0, 1, 1/2, 1/4. So it's approaching that y equals 0 because we haven't shifted it yet. So it looks like that. Okay, the next thing I'm going to go ahead and do is I'm going to go ahead and stretch it by 3. So remember, a vertical stretch by 3 means that you're going to take these vertical distances and you're going to triple them. So you're tripling all of these distances. Notice if I triple this distance, what is that distance? 8. 8 times 3 is going to go off the charts. So this point's just going to go off. So the next one we'll go ahead and do is we're going to triple this distance. This has a distance of 4, so when I triple it, it's going to move all the way up here to 12. So right now we're just doing our stretch on this guy. All right, same idea. The next one has this vertical distance of 2. Triple it, so 2 times 3 is going to give me 6. So this guy is going to have a distance of 6 right here. So we're at 6. Okay, this has a distance of 1. We're going to triple that, so that's going to move up to 3. 1, 2, 3. Okay, so a distance of 1/2. So a half times 3 is 3 halves, or 1.5. So that's going to go here. And that guy is a distance of 1/4. Triple that, that's going to give me 3/4. So still under 1, like right there. Okay, so this one, this blue one for me, and again, it's still approaching 0. This is my stretch. All right, so now the final thing I'm going to go ahead and do is I'm going to take it all and I'm going to shift it up 2. So I'm just going to take this blue guy, move it all up 2. When I do this, that also means my asymptote is going to move up 2. So here's my asymptote. It's going to approach that asymptote, so it's going to approach y equals 2. And we're going to take all these points and we're going to move them up 2. So let's see here. We'll just do black. So shift them up 2. Shift it up 2, up 2, up 2, and up 2. Okay, so connect it with a solid line. It's going to approach, but never cross. And put arrows on both sides because it is going to go on forever and ever and ever and ever and ever. All right, beautiful. So what is my domain? What is my range? So remember, domain is your left to right. So is there any value of x that's not going to work? Nope, I could put anything in for x. It all works. It continues this direction forever. It continues this direction forever. So my domain is from -infinity to +infinity. Range, we go bottom to top. So start at the bottom, nothing, 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 until I get to here. It is approaching y equals 2, but it's never going to touch it. So it's never going to touch it, so it's not included. 2 is not included. And then from here, it's going to continue upwards forever. So the range would be from +2 to infinity. Again, we're going to use a parenthesis on 2 because it's never going to actually be 2. It's just going to get really close, but never touches it. So it will never be it. All right, perfect. Okay, so let's go to example 4. This is where we're going to need a calculator. So for this question, I'm going to go ahead and use an app. This is the app I am using. So let's go to my home screen. So again, if you guys didn't see it, it's this G calculator on my home screen right here. I paid like $5 for it. It works pretty well and it's pretty similar. So the first thing I'm going to do, like normal, is reset my calculator. So you go to second plus sign, and then we just want to reset all the RAM. Let's go to the home page. So quit. So second quit will take you guys to the home page. So if I go to second memory, for a normal calculator, it's 712, and that's going to reset all the RAM, and press enter. And it says done. So it's all been reset. So again, regular calculator, you're doing second memory 712. All right, so let's go ahead and start. I'm going to write down the directions and then I'll show you how to do it on here. So go back here. Let's start writing directions. So we're looking for the best temperature for brewing coffee is between 195 and 205. Coffee is cool enough to drink at 185. Use the table below to write an exponential model. Find how long it takes for the coffee to reach 100 degrees. All right, so we have these two lists and we're talking about a statistic. So on our calculators, we're going to use the stat button. So we're going to go to stat, and then you go to edit. And we've been doing this all year, so hopefully you guys remember this. And then we're going to edit list 1 and list 2, and we're going to plug in all these numbers. So let's go ahead and do that. So we're going to go hit stat. And then we're going to go up to the top to edit. Click edit. Here's list 1, here's list 2. Type in your numbers. So 0, 5, 10, 15, 20, 25, 30. Okay, then you're going to move over to your list 2 and type in your list 2. So 204, 182, 157, 140, 126, 113, 102. Okay, perfect. Once you guys have done that, hit second mode or second quit and go back to your home screen. And let's talk about what we're going to do next. So back to our notes. So next, we're going to go ahead and turn on our stat plot. So we're going to do second, and I'm writing the directions for the actual calculator, not for the app. The app's similar enough, you guys should be able to figure it out, and I'm showing you it. So you're going to go to second, stat plot, which stat plot is over your y equals button. So second stat plot, you're going to choose number 1. You're going to turn it on, and then you're going to hit graph. And then on our normal calculator, we hit, that was a weird arrow, we hit zoom 9. And zoom 9 on the regular calculator is zoom stat, and it's going to zoom right into your stat. So let's go ahead and do this on this little app. So back here, we have, so we're going to go to second stat. So we're going to go second stat plot, or y equals. This is what the app looks like. Normally you would just go to the first one. So I'm looking at this top one. Your guys's might be like off like this. So we're going to turn this first one on by choosing L1 and L2. You can pick your graph, and now it's on and it's good to go. So if you hit graph up here, it will graph it. This doesn't have the zoom feature, so on your calculator you would just hit zoom number 9. This we can like physically zoom in. Which is kind of like hard to do. It doesn't look that nice. I keep messing up here. So I'm just going to zoom until it kind of looks like a exponential function. Okay, kind of. Whatever. Here's the things. We're zoomed in on it. It's not my best, but I tried. Okay, so now we want to find a regression line, an exponential regression. So we've done linear regressions, we've done quartic, cubic, we've done all the regressions. So now we're going to do an exponential regression that fits this data. I wish I could make this look better, like it actually looks more like an exponential. Whatever the case is, here we are. So let's go back to our home screen. And let's actually go back to our notes and let's write down the steps. So now we're going to go to stat again. We're going to go to calculate. We're going to go to exponential regression. So it should look like that. And then we need to store the regression. And on the calculator, you guys hit alpha. F4, which is up on the trace button, and then you're going to choose Y1, and then we hit calculate. All right, so on this, we're going to go to stat. We're going to go over to calculate. Then we're going to choose exponential regression, 0. Okay, and then it says list 1, list 2, and then we want to store the regression. So normally this shouldn't be in here. So to store the regression, we're going to hit the alpha button. And if you guys notice, the F4 is down here for this one. It's a little different than the calculator. So F4 and choose Y1. So you still hit that alpha F4 and choose Y1, and then we're going to hit calculate. So that's going to calculate the equation that best fits our data. So this is our exponential regression. This is actually a pretty good one. If you look at the r² value, it's 0.99. Remember, the closer it is to 1 or -1, the stronger it is. So this does have a strong correlation. So going back to our notes, let's write our regression for this. So it was y equals, our a value was 201.719. I always say round 3 decimal places unless we're talking about money. Our b value is 0.977 to the x value. Okay, so this is the best model that represents this coffee cooling down. Okay, now we want to know how long does it take for it to reach 100. So to figure out where that is, we're looking for the intersection of y equals 100. So the next thing we need to do is we're going to go to the y equals button, and then we're going to go to the y2, and we're going to equal it to 100. And then we'll hit our graph. And what that's going to do, it's going to draw a horizontal line at 100, and we want to see where the exponential model passes 100 at. And that is our answer. So going back to our calculator here, we're going to hit the y equals, go to our y2, which mine's going to be a blue color, and we're going to type in 100. Hit graph, and it draws it right in. Okay, if you guys are on a real calculator, which I am not, but on the real calculator, then what you do is you hit second, and then you go to calculate, and you hit, which is above the trace button. So if you hit second trace, that's calculate, and then you're going to choose intersect. And then it will say first curve, second curve, push enter, and then it will find that intersection for you. On this guy, we can literally tap it and find the intersection, which is funny, but so here's our intersection. If you guys look at the top of my page right now, it's probably really tiny for you, but it tells me when x is 30.2 points or 30.202, y equals 100. Well, rounding 203. So approximately 30.2 minutes, your coffee will be 100 degrees. So that intersection was 30.203, 100. So our conclusion is it takes about 30.2 minutes for coffee to be 100 degrees. All right, thank you for bearing with me with my apps. All right, so evaluate the following. We're going to do this on a calculator. So yeah, we're just using a calculator. So you're going to do e to the fourth power. We cannot do this by hand because e is this irrational number. So using a calculator, I want you guys to just type these in. So e to the fourth power, e to the -2 power, the square root of e cubed, and e to the 2/3 power. Type them into a calculator, see if you're able to get them correct. I guess I could do this as well. So if I go back to my little calculator here, go to my home screen. Okay, so E, which I don't even see on this calculator. I'm sure it's somewhere. Yeah, I don't even know where E is. There it is, e to the x. If you guys look at the ln button, so if I hit second, e to the x power, and then I can type these in. So e to the fourth power, get your answer, yada, yada, yada. So I'm just going to tell you, hopefully you had a chance to do this. So this should have been 54.598. This one should have been 0.135. This one should have been 4.482. And this one would have been 1.948. So just type them into a calculator. Easy breezy. Half-life. We can go ahead and do this. So remember on the first page we got a half-life formula. So our half-life went, our final amount is equal to our original amount times 1/2 to the, what was it? The time divided by the half-life. I think that's what it was. Yep. Okay, so let's go ahead and figure, oh, it's right here. Wow, I'm being silly. I literally didn't notice that the formula was right above us. So our final amount is equal to our original. So our original amount that we're starting with is 42 grams. So we're going to have 42 times 1/2 raised to our time. So we want to know after how many years? After 462 years. So we're going to have 462 over, and then the half-life of this element is 250. So over 250. So our K value was that 250. Our original amount was 42, and the time was 462. Plug it in. Again, we're just going to use a calculator, type this all into a calculator, and our final amount after that many years would be approximately 11.667 grams. All right, last one, finally. So this is when we're finally doing that PERT, so our continuous compounded interest. So again, A represents the amount in the account after a certain amount of time. P is our principal, so how much did we start with? R is the interest rate, the annual interest rate, and T is time in years. So make sure that we're in years. Okay, so suppose that you won a contest at the start of 9th grade that deposited $4,000 in an account that pays 5% annual interest compounded continuously. How much will be in the account when you enter college 4 years later? What I actually want to do is I want to calculate the simple interest on this and then the continuously compounded so we can see which one's kind of the better deal. Like, do we want to have continuously compounded interest or do we want to have like a simple annual interest rate on our account? So we'll split this into two and we'll do both just to practice. Okay, so this one, continuously compounded, that's when we're using PERT. So we're going to have A equals, and let's talk about what all these are. So my principal amount was $4,000. That's how much I'm starting with. My rate is 5%, so that's 0.05 as a decimal. And then my time is going to be 4. Remember, your rate, you need to change it to a decimal. You cannot use percentage. All right, so let's go ahead and plug this in. So we're going to get 4,000 e raised to the r, so my rate is 0.05, times my t, which is 4. So this is going to give me 4,000 e. 0.5 times 4 is going to give me 0.2. And again, we're going to use a calculator to calculate this because this is some crazy numbers. So this is going to be approximately, we're going to round 2 decimal places because we're talking about money. So this will give me approximately $4,885.61. Okay, so which one's going to be better for us? This continuously compounded or if it had simple interest? So now let's try a simple interest one. So simple annual interest. So that's what you should have learned in 7.1. Okay, so that's when we're going to do y equals our principal, which is 4,000. And then how much is ours increasing each year? It's increasing by 5%, but you also need to include your initial investment. So remember, this is where we have to do 1 plus our additional 5%. So we're going to do 1.05. So that's 105% because we're getting an extra 5% each year for 4 years. Calculator again. We're going to get y is approximately $4,862.03. So as you can see, they're close to almost being the same number, but that continuous compounded interest is going to be a little bit better for us. And that is going to go ahead and conclude these notes. Thank you for bearing with me and dealing with my calculator. Have a great day, everybody. Oops.